I am DC Dubey. I have been here in the physics department IIT Delhi for nearly 35 years. I shall be taking a course on basic electronics. It contains 7 units, and these units are PN diode, transistor, small signal BJT amplifiers, feedback and frequency response in amplifiers, field effect transistors, power amplifiers, and differential and operational amplifiers. This I am supposed to cover in 40 lectures. So, today we start the first lecture, which is the title is the PN diode, and this will contain a brief introduction about the semiconductors in general, and then the first thing will be how the PN junction is formed, and once the PN junction is formed, what are the properties associated with the junction, how we can calculate some of these parameters like contact potential, depletion, width, etc. So, this I shall be covering. Let us start with some few basics of semiconductors. As we all are familiar that there are two semiconductors basically, the elemental semiconductors, one is germanium and the other is silicon. Germanium has a band gap of germanium has a band gap of 0.7 electron volt and silicon has band gap of 1.1 electron volt. Of course, there are other semiconductors, compound semiconductors, gallium arsenide is also there, but for you it is sufficient if I talk about germanium and silicon. The first thing is that which of these two materials is better from device point of view. You see that germanium has a lower band gap, and this band gap is between the conduction band and the valence band. This is band gap. Now, in germanium the band gap is small. So, there are two things. One is that because of the smaller band gap, in a pure material germanium and silicon, the germanium will have a higher electron concentration. That means, the density of electrons in the conduction band in the germanium will be higher than silicon. And this is actually the carrier concentration in germanium at room temperature 300 degrees Kelvin is around 10 to power 13 electrons per cubic centimeter, while in silicon, because it has a band gap of 1.1 electron volt, this concentration in silicon is around 10 to the power 10 electrons per cubic centimeter. Now, I often ask the students that which of the two semiconductors they feel better, which is better, and many times they tell me that germanium is better because there are 10 to power 13 electrons per cubic centimeter, which is 3 orders of magnitude higher than in silicon. But I want to point out one thing, that when we make device out of these materials, these semiconductors, then there is no positive role to these electrons and holes, of course, there is no role. The electrons and holes which take part in the process of in the working of the device, those electrons and holes are obtained by doping the pure materials. That we will see, that how we get N and P type semiconductors by doping these semiconductors, and what are the other significant things associated with them. Now, so this is not the advantage for the germanium, that germanium has higher carrier concentration at room temperature or any other temperature. Another point is, because of a smaller band gap in germanium, the germanium devices will be more temperature sensitive. By temperature sensitive, I mean that the performance parameters will have a larger variation, will exhibit larger variation with temperature, and which is again is not desirable, because in our day to day life 40-50 degrees variations are very common. So, that on these 2 points we can say that silicon is a better material as compared to germanium. Now, what are how do we get N and P type semiconductors? N and P semiconductors. N and P semiconductors are obtained by doping them. What is doping? Doping is a process in which we mix known very small quantities of a external material. First, I talk about N semiconductors. For N semiconductor, we require a dopant, the material which we are going to mix with it in pure material. Remember, the doping is very minute, to the extent 1 part in a million or 10 million host atoms. So, therefore, the starting material should be should have the purity better than this. So, these are very highly pure intrinsic materials. One thing also you should remember, that in an intrinsic material, when we talk of holes or electrons, these electrons are the ones which are mobile when we apply the field. These are not bound electrons, they have come to the conduction band after breaking a bond and leaving behind a energy state, and that vacant energy state is responsible for the creation of the hole. Now, let me take one example of the N dopant, which is phosphorus. phosphorus has valency 5 and silicon or germanium, for that reason they have the valency of 4. Now, in doping, doping is in such a small magnitude that it does not change the basic structure of the host material. That means that the structure of silicon is not disturbed by the addition by the by this dopant. It dopant sits at certain lattice positions in the crystal of silicon. I demonstrate you that how we can create this n-type material. These are silicon atoms, and the 4 electrons of each silicon atom that forms a covalent with the other electron from the neighbor. For example, this silicon atom, these are the 4 electrons of this silicon atom, and they form covalent bonding from here, here, here and here. The silicon atoms are there. So, they form the covalent bonds. Now, phosphorus being pentavalent, it has 5 electrons in the outer shell. Out of these 5 electrons, 4 will form the covalent with the neighboring silicon atoms. One electron is here, other is here, one here and one here. The 5th electron, it is extra, there is no energy state available to it, and it is very loosely bound to the parental atom. How loosely bound? Actually, we can calculate as we have done it in the case of the binding energy of the electron in hydrogen, and because there the electron moves in the vacuum, here it will move in the material. So, the dielectric constant, the permittivity of the material will enter, and this permittivity for silicon, the real part of dielectric constant for silicon is around 11.5, and so this electron force to its parent atom phosphorus is reduced further by this amount, by the amount of the real part, the permittivity of the material, and it works out that this is the conduction band edge, this is valence band. There are no energy states for the pure crystal here, but when we dope it, the energy states are created here. These are the energy states of the donor. We call it this 5 group impurities as donors, because they donate 1 electron to each atom of the dopant, will give 1 electron in the conduction band. So, the energy states are here, and this difference of energy, while this is the band gap which is of the order of, if we are talking of silicon, this is 1.1 electron volt, and this is a small fraction, this is around, this difference between these two is around 0.05 electron volt. It is a very small energy. At room temperature, the electron, this fifth electron will have enough energy to move to the conduction band. This way each phosphorus atom will release its one extra electron, the fifth electron, to the conduction band. So, at room temperature kT, the thermal energy is enough, and all the dopants can be taken as ionized. You know, when we mix these dopants, they are neutral, but once it gives away its one electron, it is free to move within the material, it is not attached to the parental atom, the phosphorus. So, this becomes a ion, deficient in one electron, it becomes a ion, a positive ion. Now, there are few things which you should note. One is, in an intrinsic material, when each electron which has moved to the conduction band, it has left behind a hole here. So, therefore, in an intrinsic material, the concentration of electron and hole both are equal, and in this case this fifth electron has moved to the conduction band, but it has not left behind a hole here. So, these electrons will be extra and in excess of the electrons or the charge carriers which were present in the intrinsic material. Now, another thing important, which is very important, that in a N semiconductor, these dopant ions, they have taken a lattice, they take the lattice positions. They are immobile, they remain in the system and they do not move, but still they play a very significant role, and that we are going to see soon. Similarly, we can talk of P semiconductor. Here the dopant has to be a 3 group impurity like aluminium or gallium and so on. Normally aluminium is used. Aluminium has valency 3. There are 3 electrons in the outermost shell of the aluminium and so what will happen when we dope the material, we dope silicon for example with aluminium. Here this is aluminium, and here the 3 electrons, they will form covalent bond with the neighboring silicon atoms, and this position is vacant. This is the energy state which is vacant. There is no charge carrier here. Now, a electron from nearby silicon atom may jump into this vacant state and it will be trapped, it will form a bond with aluminium. Now, here the aluminium after acquiring a extra electron becomes negatively charged. Negatively charged ion, and again it will take the very small energy of the order of 0.05 electron volt for these electrons, nearby bound electrons, to come to this energy state. And so, these energy states are conduction band edge, valence band edge, and here, and this energy difference, this is to the tune of, as I said, 0.05 electron volt or still smaller. Now, that means this much energy is required for this electron to jump, which is available as thermal energy at room temperature. And so, electrons, these bound electrons, they move to these states to make them negative ions, and they create here holes. Again, as I said in the case of the n-type semiconductor, that each electron which was released from the fifth group impurity atom, the dopant, that was in axis and in axis over the thermally generated charge carriers otherwise. That means, as it happens in the intrinsic semiconductor. So, and here this electron, when it moves to this impurity energy level here, it has not left, it does not leave any electrons, it does not release any electrons in the conduction band. So, this material will be rich in the hole density. This is called third group impurity, is called acceptor impurity. So, we will remember that n type materials, m and n semiconductors, they have majority of electrons, and holes are in minority. And in p semiconductor, holes are in majority and electrons are in minority. Now, we can talk about the conductivity of semiconductors. Conductivity of semiconductor in general can be written as the electron contribution plus hole contribution. Electron contribution plus hole contribution. Therefore, this is Q, the charge, electronic charge, and I write here charge of electron, which is equal to the charge of hole. Sign is different, but we are concerned with the magnitude. So, charge of electron or hole, and N is electron concentration electron density, electron concentration or electron density, one and the same thing, and P is the hole density. These are they are expressed in number of electrons, for example, per cubic centimeter. This is mu n, this is the mobility of electron, and similarly mu p, this is mobility of holes, and this is expressed in practical units are centimeter square per volt per second. Now, this is the general expression for the conductivity. Now, we can write from here, we can write the expression for n semiconductor, conductivity of n semiconductor, conductivity of p semiconductor. The conductivity for n semiconductor in this expression here, the electron concentration will be much higher as compared to hole concentration. So, this term will be negligible, so will be several orders of magnitude smaller than this term. So, the conductivity for n type material becomes Q n mu n, and similarly conductivity for p semiconductor this is Q p mu p, and conductivity is expressed as in practical units ohms centimeter inverse. Now, we talk about the currents in semiconductor. There are two components of current in semiconductors. These are diffusion current and drift current. First, we talk about the diffusion current. Diffusion current arises as a result of carrier density variation. If there is a gradient, then electrons, for example, will try to diffuse from higher concentration to the lower concentration regions. This is a natural process, like when there is a smoke in the environment, then a smoke, that is the concentration of carbon particles, but then gradually they diffuse to the regions where the carrier concentration is much less. So, this arises because of the concentration gradient, and this can be represented current density due to diffusion of electrons, this we write as q dE dN by dx. This is the gradient. If there is no variation, this factor is 0, a current due to diffusion will be 0. This we can show like this. This is distance and this is electron density. Now, this is the gradient and the current, conventionally we take the direction of current flow opposite to the electron flow. So, this will be the diffusion current and this is J diffusion due to the electron. We can write a similar expression for the holes. So, the diffusion current for hole is this can be written as diffusion because of holes this is the diffusion constant for holes, this is the gradient, the density variation with the distance and this can be, this is distance and this is hole density. And this is the gradient and the current flows from higher density to lower. Current flows in the direction of holes and of course, hole movement because of the opposite charge, they move in the opposite direction to the movement of electrons. Now, with this kind of revision, we are in a position to go for p-n junction formation. p-n junction formation. If we have a silicon crystal which is doped on one side with the acceptor impurity making it p type and on the other side n type impurity making it n type, then what will happen? So, let us draw a crystal this is p region, this is n region and this is metallurgical junction. This figure is in 3 dimensional, but normally it is sufficient to draw it in 2 dimensions. So, this is p region, this is n region, this is the metallurgical junction and these are the electrons, and with them there are negative ions. These ions play a role, a significant role, important role, so we can't ignore them. While they do not take part in the charge process because they are not mobile, they are rigidly fixed at the lattice. And similarly, here there are holes and there are positive ions. I am sorry, this will be the positive ions because in the donor has donated one electron. So, these are the positive ions, and here these are the acceptor atoms which have become negatively charged ions because they acquire one extra electron. So, this is negative ions. Obviously, on the p side the density of holes is high, on the n side the density of electrons is high. For the time being we are ignoring electrons in the p region which are there in the minority, and here the holes are in minority. We will talk about them little later wherever that is required. Now, this is very important that if there is a structural continuity from the p side to the n side, then diffusion as a natural process will occur. So, holes will diffuse towards the n side and electrons will diffuse to the p side. This diffusion will not occur if there is not structural continuity in the semiconductor. That means, if we take a p type crystal separately, n type crystal separately, and just we glue them together, then this diffusion will not occur because the barrier will be so high, the physical barrier that will stop totally the diffusion processes. p-n junction cannot be formed. So, remember, p-n junction will be formed wherever n and p semiconductors are present simultaneously together and there is a structural continuity. Now, how when diffusion occurs, diffusion of holes from p side to the n side and diffusion of electrons from n side to p side. This will start as a most natural process, and what will happen when holes diffuse from here and electrons diffuse from here, they both are free. When they meet, they recombine, and in recombination what happens? If this is conduction band edge, it is valence band edge. Recombination is the process opposite to the electron hole pair generation. If this electron moves to the conduction band, a hole and a electron is generated. This is the generation process. Similarly, when holes are moving, electrons are moving, they will recombine, and in a direct recombination, if this electron meets a hole, it recombines. So, in the recombination, electron disappears and this hole is no hole then, because then it is just a bound electron like many other electrons here and so on. Therefore, due to this diffusion, a region will be created on both sides of this artificially imagined metallurgical junction, and that region will be devoid of mobile charge carriers. The situation can be illustrated like this. From this region, mobile charges have disappeared, have depleted. Where they have gone? The holes and electrons met here and both recombined, and as I just now explained that in recombination the electron disappears in the sense it is not in the conduction band, and the hole is also not there, because then it becomes a bound electron in the valence band like many other electrons. So, this region is devoid of mobile charge carriers. It is a high resistivity region and it is called depletion region. This is called depletion region. It is a high resistivity region. High resistivity region. Why high resistivity? Because resistivity of any material depends on the density of mobile charges. Now, here there are no mobile charges, only static charges are there. On the n side of this artificially drawn metallurgical junction, there is a net positive charge. On the other side, that means towards the left here, this is the n region. So, this is a depletion region, is a space charge region. Here this is neutral, there are ions here too and here the negative ions, but these positive ions are their effect is neutralized in general because of the mobile electrons. Here the effect of negative ions is neutralized by the presence of holes. So, overall if we look in any segment of the regions away from what we call the junction, this is neutral. Similarly, this is neutral, but this is not neutral. Here the charges which were neutralizing the effect of these charges, they have been depleted. So, this is depletion region, which is a space charge region, it is a high resistivity region, and actually this is junction. This is from here to here, this is junction. This is junction, and a very pertinent question, till how long this diffusion of electrons from right to left and holes from left to right, it will continue. There is another process which is coming out, that diffusion will constitute the diffusion current, but now this space charge will give rise to a field in this region with this polarity. This is electric field. Electric field, and because of these this electric field, the holes here which were in minority, they will drift towards the p region, and electrons which were in minority in the p region, they will drift towards the n region, and that will constitute what we call drift current. Now, the junction comes in equilibrium when drift current is equal to diffusion current. Here there is a equilibrium which is established, and the diffusion stops, drift stops. This thing, for more clarity, I draw another picture to summarize these currents. This is hole drift current and electron drift. So, there is a drift current in the direction of drifting holes. So, this is the drift current. Similarly, there will be hole diffusion and electron diffusion, and that will give rise to diffusion current in this direction. The drift current was from right to left, and diffusion current is from left to right, they are in opposite direction. Equilibrium has been achieved, has been obtained when the two currents, as I said earlier, when drift current is equal to diffusion current. So, we will remember the properties of the junction that junction which is called a depletion region, we can find out the width of the depletion region. A space charge region is a that gives rise to space charge gives rise to electric field. What is the amount of electric field? We can calculate that also, and it is a high resistivity region. So, all these parameters, there is a field is always that gives rise to a potential that arises because of the potential. So, what we call the contact potential. Now, contact potential, the properties associated with the junction are the field in the junction, contact potential, depletion width, and junction capacitance. Like that, these are the properties associated with the junction. We will find an expression in these for these quantities in the next lecture. We will also talk from another angle, from potential energy point of view, how what the diffusion and drift will do, and how a barrier is created in equilibrium with that will prevent the flow of holes and electrons. This is the p-n junction in the absence of any applied field. There is no external field so far we have talked. Now, one more fundamental thing I tell you, which will be required in the case of the further explanation, that when we talk of electron energy and hole energy, then we demonstrate that the electron energy increases in this direction. This is electron energy. It in, for example, electron potential energy, electron potential energy. But the whole potential energy is that goes in the opposite direction. This is whole potential energy. And why? It is just in a second I can demonstrate that this electron goes here, and if a electron goes from here, then this creates hole here, this creates hole here. So, here this is higher energy than this, meaning that whole energy goes in the opposite direction, and we will continue.